It's okay. It's okay with yeah. Okay. Good day, everybody. Thank you to the organizers for inviting me to this wonderful place and lecture and conference. I'm going to just add up to the uncle's lecture about the same phenomena, but a little bit different what you can expect from this logical reconstruction of the bands by measuring the DC and optical properties, so only fermionic transfer properties. We will see what kind of effect does this have on the reconstruction of when you measure on the reconstructed Fermi surface. What does it do with electronic dispersions? How can you see this in the transport properties which are easily experimentally accessible, especially the optical conductivity? And finally, we will say something about the possible physical systems in which this phenomena could be placed. But before we start, just to add to Danko's presentation a little bit in the maybe childish language, I'm going to give a simple explanation, actually a story about what Kadyrov actually meant by this when he came up with an idea of how to explain the emergence of the charge density wave case in the systems which have two-dimensional systems which have a closed Fermi surface. The idea was quite simple. I mean, it isn't exactly physically correct, but the story goes something like this. Imagine you have a rectangular array of atoms, okay? And in the reciprocal space, within a single Brillouin zone, you have a circular Fermi bucket, okay? Circular because you have a parabolic band-like system prior to anything topological happening. Now, the distance between the two neighboring circles in the one direction of the reciprocal lattice is such that you can place, let's say, exactly one circle between them, over here. In the perpendicular direction, in V2, you cannot do such a thing without leaving a void between the two circles, or maybe making the circles overlap if the distance is such. So we will just leave the perpendicular direction alone and inspect what's happening in the V1 direction of the reciprocal lattice. Okay, so what did we technically achieve by doing putting additional circle between the two neighboring circles? Well, for starters, we have divided the volume of the reciprocal Brillouin zone by 2, meaning that we have multiplied by 2 in the direct space. But not only that, the new wave vector of the reciprocal lattice becomes not B1, but B1 divided by 2, meaning vector Q, which is connected with the Fermi wave vector itself. It's twice as large as the Fermi wave vector. Not only that, but at the point where the bands, where the circles touch, that neighboring circles, a splitting in energy occurs, meaning that the field energy levels go down in energy while the empty ones go up. And this makes a transition between the closed Fermi surface to an open Fermi surface, as you can see, whose dimensions here in the one direction is now given by the wave vector Q. This is the reconstruction wave vector. Now the question of all questions is whether or not the gain of energy that has been obtained by pushing this closed Fermi surface to an open Fermi surface is enough for paying a bill for self-consistently forming a static lattice distortion with a wave vector Q that will in turn give you this phenomenon in the first place. Okay, and the answer is yes. The physics behind it is quite simple. You just need a classical constant humping between electrons and photons in the Pauli Hamiltonian. You have a macroscopically occupied number of photon modes within the wave vector Q, and you can basically construct this way of potential with variation with a wave vector Q, whose amplitude is given by delta and is a function of Hamiltonian coupling. You can observe how this periodic potential influences the electronic degrees of freedom, meaning that you will get the effective electronic Hamiltonian. You can diagonalize it by the unitary transformation and obtain the diagonalized eigenenergies. Okay, and if this resembles you to the usual result, then you have a nearly 3 electron gas in the vicinity of a single Bragg lane. It is precisely because it is so. You just need to change the wave vector Q, which gives you the volume. I mean, it gives you the expanse of the newly defined Brillouin zone with some arbitrary wave vector K. But now you can ask yourself a question whether or not in this scenario all this happens when you have in two-dimensional, three-dimensional case, the system which two neighboring Fermi surfaces are exactly another Fermi surface apart? Well, the answer is no. I mean, certain values for the parameters entering in the Hamiltonian have to be met. And as you can see, this restriction is a little bit severe in the three-dimensional than in the two-dimensional case. Okay, so way to maybe some kind of recipe where to search for this effect is actually in the two-dimensional systems. Okay, once you have the bands and you want to make this, well, approach this analysis as general as possible because you're dealing with the three-dimensional, two-dimensional case, is to redefine your Brillouin zone in respect to the reconstruction wave vector Q. You have something that is parallel or perpendicular in the Brillouin zone to it. You can rescale the block wave vectors by dividing it by the reconstruction wave vector, introduce a very useful energy scale of the electrons and eta parameter, which will give you the ratio between the static deformation and the electronic degrees of freedom. You can expect it to be much lesser than 1. So, doing all of this, you can find how does the band slices in energy look like, because once again, you cannot change the Fermi level itself. It is strictly located within the pseudo-gap region because, again, Fermi wave vector defines the wave vector Q, which in turn defines the Brillouin zone and the bands itself. But you can give some kind of idea how the band looks like with equi-energy slices here. Notably to say, there are 4 characteristic points in this two-band system, which will give you the extent of the two-band model itself between omega t and omega b, and the width of the pseudo-gap region between omega u and omega l. Once you have the bands, it's only naturally to calculate the single particle density of state. So as you can see, nothing spectacular happens when you are far away from the pseudo-gap region. You obtain the two-dimensional, three-dimensional free electron and gas density of state. But within the pseudo-gap region, well, there is a difference. You have a flat density of state, constant density of state in the three-dimensional case. In omega L point, which is here, Lifshitz singular contribution to the logarithmical contribution to the density of state occurs, and so on. Only for the three-dimensional case, you are able to write analytically the density of state. Okay, moving to the first of the experimentally accessible data is the DC through the weight, which is proportional to the effective concentration of charge carriers. Again, we cannot change the Fermi energy. It is located within the pseudo-gap, but in essence, the concentration, the effective concentration, is some kind of spatially dependent quantity, which depends also on the Fermi level. And for this particular system where you have your parabolic band in the first place, the result is that the effective concentration in the parallel direction to the reconstruction wave vector significantly differs from the effective concentration in the perpendicular direction to the reconstruction wave vector. By the way, for this particular model, at the pen perpendicular is actually given to the total concentration of electrons for two-dimensional and three-dimensional case. Now, this figure should be looked upon indicatively. So, if you will direct your electric field, let's say parallel to the reconstruction wave vector, you should get in two-dimensional case a factor of 3 times reduced value when you measure DC conductivity when compared to the perpendicular direction, a factor of 2 if you're measuring in the three-dimensional case. The same applies for the Zagreb coefficient, namely the thermopower, because once you have the effective concentration, the thermopower you get for free. Basically, you just take the derivative of the effective concentration. And it's also indicative because, as I said, you cannot change the Fermi energy a lot, but you can, from this figure, conclude that it's negative thermopower in the two-dimensional case when you're parallel to Q. It's finite positive when you are opposite to in the direction of Q. It is 0 in three-dimensional case where you're in the direction of Q, and finite when you are perpendicular to it. And now something that is easily measurable, optical conductivity, and by this I mean inter-band conductivity. So you can always start with the general expression of the irreducible current dipole correlation function, with the full dressed fermion lines, full vertex representation, and so on. But I'm going to approximate this with a single loop approximation in which I only have the contributions of the inter-band matrix element, current matrix element given here in orange color. In the approximation, when you don't have any kind of inter-band scattering, you can analytically derive a simple form for the real part of the conductivity. As you can see, it also has some kind of a spatially dependent index alpha, which is connected with the same index alpha in the inter-band current matrix elements, which, by the way, can be obtained from the Hamiltonian, your electronic Hamiltonian. And for this particular model, their value is given by this expression here. Now, the consequence of using free electron models, free electron dispersions in the first place prior to the topological phase transition, is such that only longitudinal component in optical response survives. If we had used a linear dispersion, we would also have a perpendicular component of the optical conductivity. So again, we are making things simple by dividing the incoming photon energy by the electronic scale and defining the limit of the optical conductivity based on the limit of the two-band model, and so on, introducing some auxiliary functions which will be very useful. We get the final analytical result for the d-dimensional real part of the optical conductivity, so for the two-dimensional, three-dimensional case. The overall significance is that this constant is universal. I mean, it goes the same for the 2 and 3 case, has the same thing that is proportional to the eta squared. So if eta is small, squaring it is even lesser. So it's not a big optical response. But then again, you have an overall for large enough values of omega decay, which goes like omega to the minus of third. So it's fast decaying function of frequency. Again, Fermi energy is fixed, but here we're going to nonetheless investigate what happens if we, by any chance, would leave the Fermi energies, leave the electron dispersions as they are with the same wave vector Q, but expect what changes to the optical conductivity as we can change the Fermi energy itself. And there are 3 cases about what really can be happening. So if you put the Fermi energy below the pseudo-gap region between omega B and omega L, the common theme for the 23-dimensional optical conductivity is such that it is a finite function of frequency, so no divergence whatsoever. It is bounded by the Pauli edge on the left side, meaning that the minimum vertical distance between the lastly occupied and the first empty state in the upper band. And as you can increase the Fermi energy, the area under the curve increases as it should be, and it moves towards the minimal value of omega mean, which is just the weight of the pseudo-gap. That's the threshold beyond which there is no going more to the left. In the intermediate case where the Fermi energy is located in the pseudo-gap, and that's the realistic case we are dealing with, so this is experimentally observable for this kind of a process. What happens? Well, in 2 and 3-dimensional case, now you have a 1 over square root type of the divergence of the real part of the conductivity. The origin of such a divergence is quite easily to understand, namely, in the k-perpendicular directions, both bands, the lower and upper, are parallel to each other, and they are distant by 2 eta, so omega min apart. Meaning, as soon as you get Fermi energy a little bit above omega L, there is finite number of states filled, which can be excited to the equal number of empty states by the same energy eta, giving us the singular response to the optical conductivity. Again, by increasing Fermi energy, area under the curve increases. And the final interval of inspection is the third, when the Fermi energy is above the upper value of the pseudo-gap region. Again, you have the presence of the divergence, because the same scenario applies here as in the previous case. But not only that, in the overall shape of the conductivity, you have some kind of kinks into a 3-dimensional case, which are connected with this vertical transition, but now in some kind of different fashion. And in this regime, you can also define the critical value of your Fermi energy, upon which the third band is needed if you want to excite electrons away further to the upper energy unoccupied levels. But since we are in the two-band model, this is also a restriction to the applicability of the two-band model without needing a third band to explain your optics experiment. Now, what kind of optical experiment would it be if there is no sum rule in this game? And you can easily check that the sum rule is actually obeyed within this simple model. I myself did not know that this might be true, but then again, you can easily check it out to be. So basically, what does it say? It says that the total concentration of electrons which you have started with has to be somehow distributed over all possible means of excitations. Either it is intra-band, so the Rukelj contribution, or all optical excitation, so it's the integral of the optical conductivity. So putting it blindly, when you do the integral, you wind up that total is effective concentration plus this integral of the real part of the optical conductivity. Of course, everything here is the function of the Fermi energy, and by subtracting this element from this element, for the two-dimensional case, is giving basically the distance between the red and the blue curve. As you can see, this red and blue curve, the length corresponds to 99% of exactness to the integral below the Fermi, below the optical conductivity curve for corresponding values of the Fermi energy. This is so because, to be honest, the real part of the conductivity goes to the power of omega to the minus 3, and this integral, when you integrate it to the top of the applicability of the two-band model, basically collects everything there is below the area of the curve. You don't need to go to the infinity in order to do that. There is a general sum rule stating the same thing, but it uses multi-band approach and, of course, the generalized current matrix elements that we have mentioned before. Is there a possible system for two-dimensional system for this emergence to be founded? Well, you need a parabolic band. You need it to be a little bit like two-dimensional because of the constraint in forming open Fermi surface. And the one thing that I know is there is a class of the two-dimensional heterostructures which are comprised of a sandwich-like form. You have two layers of hexagonal boron nitrate between which there is a layer of alkali atoms. Okay. Now, depending on the type of alkali atoms, is it lithium, cesium, potassium, whatever, up to depending on that type, and the configuration, meaning that looking from above is every hexagonal void occupied by alkali atom, every other, every third, and so on. So there's a configuration. You will get, of course, a parabolic band within your hexagonal brilliant zone, whose area, I mean, the Fermi vector depends on the type and the configuration of the alkali atom. So let's say that you have a perfect match of alkali atom and corresponding configuration. So you don't have the scenario given in red, you don't have the scenario given in green, but you have the scenario within the hexagonal regional zone given in blue. So the two neighboring are only a circle apart. You can basically do the same reconstruction procedure, but now you don't have one, you have rather three reconstructing wave vectors, and you have transition it from the closed Fermi surface to the closed Fermi surface once again in this particular hexagonal example, whose area is exactly 1/4 of the starting brilliant zone. So if you're going to, let's say, put your electric field in the direction of one of those reconstructed wave vectors, you should get an optical response and the DC response which are comparable with the analysis done so far. Okay, and in summary, we have shown what are the DC and electronic transport properties of such a system that undergoes a topological reconstruction of its Fermi surface. But there are a lot of things that have been unanswered here. So, for example, we have to really calculate the effects of the biaxial and triaxial potential in optics and in the DC transport. What about when you have a linear like graphene like dispersion in the first place? this extra perpendicular component to the optical conductivity is present, how does it behave? Of course, there is effects of the condensate that might contribute to the transfer properties, finite temperature effects. And of course, there's always a need, as Dante said in the previous lecture, but if you have multiple Fermi pockets within your baryon zone, which will be ellipsoidal, circular, how do you generalize this kind of approach in dealing with such a phenomenon? So that's all. Thank you for your attention.
Could you please explain if your reconstruction process requires superposition of the Fermi level and you shifted it outside of this optimal region, what could prevent the system to be reconstructed?
Oh, that's a good question. I'm thinking maybe some kind of a pinning should be, just some kind of a interaction with impurities and so on. I mean, I can imagine that Fermi energy in exact calculation isn't in the middle of the pseudo gap anyway, but I'm sure that system might allow us to change it not much within the pseudo gap that we remain, but not much than the order of magnitude within the delta parameter itself. So I'm not saying that they should go below the pseudo gap region itself, but if you can, but this model, basically, this conductivity form here, is a general form of conductivity of any kind of dispersion in the vicinity of a single Bragg plane, and it has an analytically derivable result. So the value of it is already here to some extent. What's the yes, in the starting. Well, no, it's not. I mean, there is a question: what happens if you start with a linear dispersion, and that's something to be looked upon. I mean, there is a difference, so we know that this is going to be different. So you will have also not here parallel, but also a perpendicular component. But we started with the parallel because there's actually systems in two-dimensional case which can be, for example, not only this one, which have a parabolic like dispersion, so it might be accessible to the experimental verification.